All right, today we are talking about special right triangles, and it's a really short little unit here. And really, today we're talking about some background information you need so that tomorrow we can talk about what special right triangles really are. So today we're mainly going to focus on Pythagorean theorem review, and we've been using it a ton this year, but we're going to dedicate some more time to it because we're going to need it. We'll be using it a lot in this unit with special right triangles. So Pythagorean theorem works on any right triangle as long as there is a right angle. And it means that the square of the legs is equal to the sum of the squares of the legs is equal to the hypotenuse squared. Most of you know this already. Like I've said, we've been using it all year, but we have a squared plus b squared equals c squared. That's our Pythagorean theorem. A Pythagorean triple. So we might not have gone back over this vocabulary yet this year. That's when all three sides of your right triangle are whole numbers. So it's really kind of a special case, and to denote that, we call them Pythagorean triples. So 3, 4, 5 is your most famous one, 5, 12, 13. And then any of those triples, if you multiply them by the same factor, would also be a triple. Like if we took 3, 4, 5 and multiplied it by 3 and had 9, 12, 15, that's also a triple. Okay, so just some basic Pythagorean theorem here, and we're going to leave everything that we can in simplified radical form instead of decimals because it will be more accurate. So if it comes out to be a whole number, great. If not, we want to write it as a simplified radical. So here they give us the two legs, 5 and 12, and we're solving for x. So I have 5 squared plus 12 squared equals x squared. 5 squared is 25. 12 squared is 144. So that'd give us 169. Which is a perfect square. So when I square root, that'll give us 13 is that missing side, right? And this would be a Pythagorean triple. Now on B, they're giving us simplified radical sides. So I have a leg of root 7, a leg that's x, and a hypotenuse of root 19. Now remember, square roots and squares are opposites. So this will come out to be 7, and this will come out to be 19. So then from here, I want to subtract 7 from both sides. So then I want to take the square root of 12. And to do a simplified radical, we want to pull out any perfect squares we can. So factors of 12 are 4 and 3. And I want to pull out 4 because it's a perfect square. So my final answer here is 2 root 3. Or your DI30 will simplify those for you, but you should know where they come from. Example 2, find the length of the sides of a rhombus with the diagonals having a length of 12 and 30. So when we are learning about quadrilaterals, we know that the rhombus diagonals bisect in a 90-degree angle. So if one diagonal is 12, that would be 2 pieces of 6. And if one is 30, that would be 2 pieces of 15. But really, I have a right triangle in here with a leg of 6 and a leg of 15. And then I can solve for the hypotenuse. So I'll do 6 squared plus 15 squared equals x squared. So 36 and 225 would be 261. And if I square root that, it looks like 3 root 29 would be our simplified radical. And if I wanted to add a step in here, that's really because we have 9 and 29 are factors of 261 for x. All right, so that'd be the side of our rhombus. In an isosceles triangle, the base is 24 inches long. The altitude to the base is 5 inches long. Altitude means from the tip of our triangle to the base. So they're saying that this would be 5. Find the length of the legs of the isosceles triangle. So this altitude will divide our base in half, so you'd have 2 pieces of 12. So you have 5 and 12 as your legs, which we've already done actually. We did that as part A of example 1. So our hypotenuse would be 13, where the sides of that isosceles triangle would be 13 inches. We should include units. So I think that's the only one that had units so far, 13 inches. You place a 10-foot ladder against a wall. So this will be my wall. Here's my ladder. Okay, 10 feet. The base of the ladder is 3 feet from the wall. How high up on the wall does the top of the ladder reach? So pictures always help in these kind of scenarios and often will require a picture on a quiz or a test. So it looks like I'm looking for a leg, but I have one leg that's 3 and a hypotenuse of 10. So that'd be 9 and 100. Subtract 9 from both sides. So that's 91. And it looks like there's no perfect squares that come out of 91. So we'll just leave it as x equals root 91. All right, moving on to the back side. 3D Pythagorean theorem is something we haven't reviewed yet this year, but you've probably seen before. It's something that I work with my Math 8 students on in the spring. 3D Pythagorean theorem is a rectangular prism, so that's a 3D shape. The longest length within that rectangular prism is diagonal from one corner to the other. Okay, that'd be the longest length in this whole prism. And I'll kind of try to draw in some dashed lines here, so it looks a little bit more 3D. But from the front corner to the back corner, diagonally in that box, would be the longest length in that rectangular prism. And what happens is really what we're doing here is we are finding Pythagorean theorem twice. So I would want, let's say on the base here, I have a 3, 5, something right triangle. Okay, I do 3 squared plus 5 squared equals this piece right here. Okay, and this hypotenuse of the triangle on our base is going to be a leg of this triangle cutting through where we can actually find the length we want. So 3 squared plus 5 squared equals c squared. So 9 plus 25 is 34. So we'll go ahead and leave that as root 34 equals c. Okay, so now I know this piece right here is root 34. And I know that the height right here is 15. They gave us that. So I want to do Pythagorean theorem again so I can find the hypotenuse, except this time I have a leg, and I'll go ahead and sketch this larger triangle here. I have a leg of 15, a leg of root 34, and I'm trying to find that hypotenuse that's cutting through my rectangular prism. So I have 15 squared plus root 34 squared equals x squared. So I have 225 plus 34 is 259. And it looks like that doesn't simplify, surprisingly. So root 259 would be our final answer there for x. Now that is how you would do it if you're only using normal Pythagorean theorem. You would do it twice, and that's really why it works. But you could also do, we call it x squared plus y squared plus z squared equals c squared, where you plug in your 3, your 5, and your 15. Okay, this will also get you to that root 259, and it's quicker, it's more efficient. But the reason this works is because of this process, the longer process. So before just giving you a shortcut, I want to show you really what's happening here. But this would be the shortcut for 3D Pythagorean theorem. Okay, and let's go ahead and label, this one was centimeters. Centimeters, final answer. Okay, converse of the Pythagorean theorem is when it gives you all 3 side lengths, you can plug it in to our Pythagorean theorem. And if it's true, it's a right triangle. If it's not true, then it's not a right triangle. So determine if this is a right triangle. I believe our hypotenuse is our longest side. So 8 would be our hypotenuse. So we have 4 root 2 squared. And I'm going to go ahead and put that in parentheses so I don't forget to square both. Plus 4 root 2 squared equals 8 squared. So that'd be 16 times 2 is 32 plus 32. That's 64. 8 squared is also 64. So since it's 64 on both sides, that's true. It is a right triangle. Okay, if it was not the same number on both sides, it would not be a right triangle. Last thing we want to talk about quickly here, I know it says notes 2, but we're combining 1 and 2 since 2 is so short, is rationalizing a denominator. So in order for something to be considered simplified, it cannot have a radical in the denominator of the fraction. So we need to get rid of those in order for it to be nice, neat, and as simplified as possible. So to get rid of that, like this is 4 over root 5, that's not considered simplified, we can multiply both the top and bottom by root 5 over root 5, because really in reality we're multiplying it by 1 when we do that, which doesn't change our final answer. So I'd have 4 root 5 on the top, root 5 times root 5 is 5, and now I don't have a radical in my denominator, and this would be considered simplified. So for this one we would do times root 3 over root 3. So since they're both in a radical, we multiply underneath. 5 times 3 is 15, so we have root 15. And then you'd have 3. And you're also going to want to make sure that you're simplifying if you can. Root 5 is as simple as possible. Root 15 is as simple as possible. Another thing you might want to check before you start multiplying is if you can simplify before you multiply anything. So on this last example, root 6 over root 27, I could pull a 3 out of both. So if I divide both of these by root 3, it'll make it easier to work with, where I'd have root 2 over root 9. And honestly, root 9 is 3. So sometimes you can make it easier on yourself by pulling out a common factor or simplifying in the beginning. It just keeps everything smaller. But if I didn't know that and I multiplied by root 27 on top and bottom, I would still end up here at the end. It just might take me more steps. So that's it for our notes for today, and then we're working on worksheet. It's just labeled worksheet 1, but it has some from both Pythagorean theorem and rationalizing a denominator, and then tomorrow we'll actually just work on section 3 and do worksheet 3. So there's no individual worksheet 2.